Good afternoon and welcome to today's lecture on algorithms and data structures. Last week, we continued graphs and looked at the lowest cost search, which is an extension of our shortest path, and we assign costs to actions. We saw how to implement this algorithm, compared it in detail to shortest path, saw why this generalized search in a state space is very helpful and reusable. And then we looked briefly at A star, and I gave you a few general hints on what you should pay attention to when you work on graph problems. Then we started with the complexity analysis chapter, and that's the one we will also finish today. We first of all wondered how we can measure the running time of an algorithm, and we saw that this can be done, but it's not very reliable and comes with lots of challenges. So what we want instead is we actually want a mathematical approach to determine the complexity of an algorithm that is based on counting the number of primitive operations for which we assume that they are all equal in terms of the running time. And for every algorithm, eventually what we want is a function of the input size. And this is the one that for which we will count the number of primitive operations. And we will always focus on the worst case input. And we saw potential primitive operations, and we will focus on the worst case input because optimizing for the worst case input typically leads to better algorithm for all inputs. And we saw some sample functions, some basis functions that we will from now on use in our framework, like a constant function, the logarithm function, linear function, quadratic function, n log n, as well as polynomials and the exponential function. And we saw in that order that they grow faster and faster. And today we actually want to build a framework in which we can come up with such functions for our algorithm. We have already started with this. We looked, for example, at the maximum value function, and we wondered where it spends most time in. And that's in fact in the loop, because we always assume worst case big inputs, so not just an empty list, but actually a larger one. And we see then most of the time would be spent in that loop. The other work for initially accessing the first element or returning something are then negligible. We started introducing this O notation here, and today we will actually define it and we see what it's useful for, and then we will start applying it to algorithms, and then we have a framework we can use to determine the complexity of algorithms. And in addition to this O notation, there are a couple of other notations that will all become quite easy to understand once we have started to introduce O. And I will show you this on the whiteboard now. So we will introduce the O notation, or sometimes called the big O notation. And what we want is we have functions f of n and g of n. And these are functions that map positive integers to real numbers. It's I've written all of this down in the slides, but for here on the whiteboard, I just put the essence there and the rest orally. So these are functions that map positive integers to real numbers. And we say f of n is O of g of n if there is a real constant c that is greater than 0 and an integer constant. So here I can write real constant c and the integer constant n0, which must be greater than or equal to 1, such that the following inequality holds true, and the inequality would be f of n is less than or equal to c times g of n. For all n's that are greater than or equal to n0. So what does that mean? So we have our mappings f of n and g of n that map from positive integers to real numbers. We say f of n is O of g of n. And for this, we also need some constants, which are z, that is greater than 0, and an integer constant n0 that must be greater than or equal to 1. And then, in order for f of n being or O of g of n, we need to see that this f of n is less than or equal to the constant c times g of n for all n's that are greater than or equal to some threshold n0. Typically, we don't always say big O, we just say O. So you would say f of n is O of g of n. Some people may say f of n is big O of g of n because there's also a small o. But typically, we would just say O and not always big O. And what does that mean now? We can try to visualize something. So we can have the input size on the x-axis, input size, and we will have the running time. And the running time in terms of the primitive operations later. And we say that f of n is O of g of n. And we will have our function f that could go something like this. And our c times g of n could look something like this. So the red one is c times g of n. And we have our threshold, which is the n0. And what we see is, that's what we just wrote up there, is that f of n is less than or equal to c times g of n for all n's starting at some threshold n0. We can clearly see that this holds true here. Initially, maybe f of n is, so in this region here, f of n is greater than c times g of n, but starting some threshold, f of n is less than or equal to c times g of n. And if that holds true, we say our f of n is O of g of n. Who of you has seen something like this before? Maybe in high school or when you studied computer science on your own. Maybe a thumbs up, green sticker if you have ever seen something like this, or red sticker if you have never seen anything like that. So one person has seen this before. Maybe you want to tell us either orally or in the chat where you have seen this before. And while we're waiting for your answer, we'll go ahead with an example. We can say that the function 8n plus 5 is O of n. So this here would be our f of n, and the n here would be the g of n. And we got the answer in the chat. One student says he has seen this in a Python course a few years ago. Good. We will introduce this concept now, and then we will see why it's actually relevant to programming and algorithms. So, do you think that this holds true, that 8n plus 5 is O of n? If you think this is true, green reaction or thumbs up. If you don't think this holds true, send some opposite reaction. We only got positive responses, and this holds true. And why does it hold true? So we need to find a constant c that is greater than 0, and we need our integer constant n0 that is greater than or equal to 1, so that our 8n plus 5 is less than or equal to c times n, because this was our g of n, which is just n. And this needs to hold true for all n that are greater than or equal to n0. What we can pick as a solution is, for example, we could say we don't need to find the minimum values for c and n0. We could say c is 9 and n0 is 5. Because what we would have then is, we would have something like 8n plus 5 is less than or equal to 9 times n, because this was our our g of n, and this is the constant, and this would hold true, for example, for all n's that are greater than or equal to n0, where our n0 needs to be greater than or equal to 1, and here it's 5. This would hold true. It's maybe not the minimum values, but with this O framework, we also don't require for n0 the minimum value, but rather we can pick some n0 for which this relation holds true. Would you have a different suggestion, like another possible solution? There are infinitely many ones that we can pick for C and n0. If you have a different solution for which this relation holds true, maybe send it to the chat. I want to see if you got the concept. And as I said, it doesn't need to be the minimum values, just some threshold and some constant for which this holds true for all the subsequent n's. One person said something like, "Ooh, I think this is maybe a bit more complex what you wrote there. Maybe you want to simplify this or have some simpler ones, because you gave us some with some fractions and something. It can certainly be easier. Anyone has a different suggestion, some easiest possible solution. So this is solution number 1, and I want solution number 2. So C and N0. Well, since there are no solutions from your side, I could also say my N0 is 1 and C is 13, because then we would have the 8n plus 5 is less than or equal to 13n, and this applies already S of n equals, or n0, that is 1. So there are infinitely many solutions for this. And why is this O notation relevant to algorithms now? What we want is, and I'll just switch to the slides for that. So what I wrote here is just a written out definition of the big O notation. It's exactly what I had shown you before, just wrote out it's mapping positive integers to real numbers and so forth. And this is the plot we had looked at. And also possible solutions for the terms we had just looked at. So why is this O notation important? We can say with the O notation that it allows us to say that a function f of n is less than or equal to, so f of n is less than or equal to another function g of n up to a constant factor and in the asymptotic sense as n grows towards infinity. Asymptotic here means for ever larger n's when n grows towards infinity. Maybe not for very, very small n's. That relation may not hold true, as we saw here. For very small n's, the relation does not hold true. But for large n's, yes, the one starting from the threshold. And that's why we say this g of n is also sometimes called an asymptotic upper limit or asymptotic boundary of f of n because it constrains f of n for large values. Sometimes we also say f of n is the order of g of n. So the g of n is like an upper boundary. But mathematically speaking, we would actually need to say that f of n is an element of O of g of n. Because technically speaking, this O notation denotes a whole collection of possible functions that are upper boundaries of f of n. What you will also see sometimes in the literature is something like this. In the literature, you would sometimes see that people write out something like f of n is equal to O of g of n. This is only written there for convenience in those sources in the literature. It's not an equation, because if it was an equation, you would be able to also swap them and you could say O of g of n is equal to f of n. That's not true. So technically speaking, this equal here is just a simplification for convenience, and actually you need to put an element sign there. And if this is not a proper equation, you cannot just flip it. So flipping it like this would be totally wrong. So what I like to say, and I think that's also what the Goodrich book does, is the notation is you say f of n is O of g of n. Ideally, in this course, you would avoid putting the equal signs in and write f of n is O of g of n. You can use this equals one if you want, but make sure it's not an equation for which you can swap these two elements. In this course, I tried as far as possible always write is and not have an equal sign. If there is an equal sign somewhere, maybe there's a minor lack of consistency, but I try to always write out f of n is O of g of n. But if you look into other sources, they often use or sometimes use this equal sign. Now we have introduced this O notation. We've seen how it works, but always finding a proper C and N0 is quite boring. And it turns out we can generalize this and we can use this O notation to simplify terms. What this means is concretely, imagine we have a term like 5n to the 4 plus 3n cubed plus 2n squared plus 4n plus 1. What we want is an upper boundary. And we can ignore constant factors because we say f of n must be less than or equal to c times g of n. And you've seen before in this course, like last week, we don't care about constant factors in our complexity analysis because constant factors are something that doesn't really matter in the theoretical framework because maybe one computer is just as the double speed of another one. But what we care about is what the number of or how the number of primitive operations in an algorithm keeps growing as n gets bigger. So we don't care about constant factors. And in fact, with this O notation, we only care about the largest term because this is the one that determines most the number of primitive operations. So if this was an analysis of some algorithm and we make n very, very big, then this would be largely driving the number of primitive operations. So we can say this term here is O of n to the 4. And what we want to do from now on is we want to count the number of primitive operations in an algorithm, come up with terms like this, depending on n, the input size, and then use the O notation to simplify this. What we have is an upper boundary, or the order of which the number of primitive operation keeps growing. So we can ignore lower order terms as well as constants. So you will have a quick task here. I want you to look at these next five examples, and I want you to think about what their O complexity could be. And I will quickly copy paste this to the whiteboard. And in a moment, we will continue. So just take a short moment to think about these next five examples, what their O complexity could be. So now that you had a few minutes to think about these terms, so we look at 5n squared plus 3n log n plus 2n plus 5. What is its O complexity? You can turn on your mic or tell us in the chat what you think, what O complexity that term is.
I think it's for the first one, it's n squared
Yes, that's correct. And why?
because it's the most one that impacts the like the function.
Yeah, the number of
Like it
primitive.
has a larger, yeah, it has a larger impact n squared than n log n and n.
Exactly. For large n's, this is the one that contributes the most, and then we can remove the constant 5 because we don't care. Good. Then the next one. One student suggests it's n cubed, and that's correct because this is the largest term and the constant gets ignored. The next one is 3 log n plus 2. It's O of log n. And it's very important in this course, you always write O of something. You wouldn't just write n squared because that would be wrong because we use the O notation. And also the basis of the log doesn't matter. We've seen this last week briefly. We will always just look at log. The exact basis is just a constant. And the very last one is 2n plus 100 log n, and n contributes the most. And now I have skipped one, and I want you to think about what could be the O complexity of 2 to the power of n plus 2. Any suggestions?
Is it 2 to the power of n?
Yes, and why?
Because you just ignore the constant, which is plus 2, since it doesn't impact as much as 2 to the power of n.
Yes, ideally, you wouldn't just ignore the constant, but you can write out this. So it's 2 to the power of 2 times 2 to the power of n. That is the constant, and you can ignore it. So it's O of 2 to the n. Perfect. So, there are a few things you need to bear in mind when it comes to this O notation. You can obviously pick much larger upper bounds, like you can say 5n plus 3. Obviously, c times n squared is an upper boundary for some threshold. Obviously, 5n plus 3 is the order of n squared. It's correct, but it does not provide any reasonable insights. I always wanted to pick reasonable boundaries. And if you obviously could pick also an exponential boundary, but eventually we want to be using this to compare algorithms. And we want to, if say we have different algorithms for the same computational problem, that we want to compare them in terms of their O complexities, and we need to find reasonable bounds. And if you're asked in the exam to find boundaries, find reasonable ones and not just unnecessarily large ones, because they will not help us to compare these algorithms. You can also write stuff like, for example, 2n squared is O of 4n squared plus 6n log n. That is true, but it really, again, does not provide any reasonable insights and doesn't look fashionable. So if you have something like 2n squared, you would say it's O of n squared and not something like this. It's correct, but not fashionable. Now it looks like we can just ignore lower order terms and constants. We do this in our framework, but eventually they still have impact on the execution time. So it could happen you have two algorithms and maybe one has a better complexity than the other one, but it runs slower than the one that has a great or bigger complexity. Simply because maybe your algorithm that has this lower complexity has a lot of higher order terms, very large constants, and for the input size you're looking at, maybe the algorithm with a larger complexity runs faster. This can happen. But overall, when you implement algorithms or design your algorithms, always aim for low complexity and eventually good speed typically follows. Maybe for small n's or something, there can be exceptions to this. We will also see some algorithms in a few weeks in which maybe the input size needs to be massive for that algorithm to actually run faster. But most of what we do in this course is really aim for low complexity and good algorithms will follow. Complexity is not the only thing you need to look at. Also running time eventually, even if you tell your customer, oh, my algorithm has good complexity, but it still takes 10 seconds to show an update in a user interface, is also not great. So maybe you would also come up with maximum running times for specific inputs just to not let your customer wait. But this is all secondary. First of all, aim for good complexities and good algorithms typically follow. We will now look at an algorithm problem. And for this, we will try to, and there's a question here, is if the O notation, is the O notation a limit of a function somehow related? Maybe you can rephrase the question so we fully understand it, because I don't think from the grammar it makes totally sense. And then we'll come back to your question. We will now look at something that is called the prefix averages. It's just a minor computational problem, but we will try to implement it and step by step reduce the complexity and then implement it with the minimum complexity possible. So what are the prefix averages? I'll just show you an example. So we have a sequence prefix averages. We have a sequence S of n numbers, and we want to compute, so this would be the input, and the output, we will have a sequence A for which our aj is the average of elements S0 up to Sj. I'll show you this now. So we have a sum for index I is 0 up to j. We take the input at index j and we divide by j plus 1. And our j has indexes 0, 1, 2, and so forth, up to n minus 1. What does that mean? I think we can look at a simple example briefly. So we have, say, sequence So we have S that is values 5, 2, 3, and 1. So we have n inputs. And I want you to think about what A could look like. So A, 0, because J starts with 0. What would be A0 if I use this definition to compute AJ, where J is now 0? Got the right answers, it's 5. Because all I'm doing is I'm taking this 5 and I'm done with the sum, and J is 0, and I divide by J plus 1, so I just divide by 1. What is A in index 1? Got already the right answer. It's 5 plus 2 divided by 2. So it's 7 divided by 2. It's 3.5. And next one, we can say A2. What is A2? It's 5 plus 2 plus 3 divided by 3. So it's 10 divided by 3. So it's 3.3. And so forth. So this is the prefix averages. What we want to do now is we want to implement this, come up with an algorithm, and then see what its complexity could be. And we will start with a very naive implementation of the prefix averages. So we will call this the prefix averages 1. And we have an input S as our sequence, and I need to know what's the length of the sequence. And in Python, we've seen this before. We assume S is just a list. We look at the length of the list. And I want to have an output, A, that I want to return. Oops. So A will be an output that I'm returning, and I'm returning A. Now, A will also have length n. I could just create an empty list. That's correct. But then I need to append to the list, and later we will see the list will just keep growing, and this will lead to extra work. So we will just create a list up front of size n. And what I can do is I can have a list with just 1 0 in, and I can say multiply this with n. And what this creates is a list of length n that only has zeros. So, because in the next chapter, we will see how lists work and the work that happens when we start with a small list and then keep growing the list, because that also leads to some computational work, which we will see later. But for now, we just create once that whole list that we need. Now I can say I go through all the j's in the range of n. So j starts from 0, 1, 2, 3, up to and including n minus 1. I can say this is my total. And now I'm trying to build that sum we've just defined before. I can say I go through my I, which goes from 0 up to j. We've said I is 0 up to j, but if I want to go in Python from 0 to j, I need to put in the range j plus 1 because it's an asymmetric boundary, and it starts implicitly with 0. So I can say, well, I'm adding something to the total now. I'm adding the si to the total. And once the inner loop is done, at the end of the outer loop, I can write aj is the total divided by j plus 1. We can call the prefix averages now just on our sample data set from before 5, 2, 3, and 1. And we just get the numbers from before. We didn't calculate the last one, but these numbers are the ones we expected. So what is the complexity of that algorithm? Maybe without looking at the slides, do you have any hint what the complexity of this algorithm could be? O of what? If you have a guess, send it to the chat, please. So one person guesses O of n squared. We will look at that now, if this is true. We will investigate the algorithm step by step. What is the complexity of the first statement? Or how many primitive operations do I need for the first statement, where I look up the length in S and store it in N? And maybe turn on your mic, I'd like to discuss this with you and see what you think from the work we have done before, what kind of complexity this could be. So one person suggests O of 1 constant. Yes. In fact, I have two primitive operations. I have looking up the length and then storing it in N, but we just say constant. And the last line is also constant because we are just returning something. The line 3 is O of n because I'm creating a list of size n, and creating that list cannot be done in constant because it's subject to n, and n is a variable. It's not a constant. And then this eventually takes O of n time. Now the body of the outer loop is run n times, because I say it's the range of n starts with j equals 0, 1, 2, 3, up to n minus 1. So this is run, the outer loop is run n times. So this line, total equals 0, and the last line in the loop, aj equals the total divided by something, all of this is run n times. This one here is run n times because the loop runs n times. This is just a constant operation. And here I have a few constant operations. I divide the total by a sum. So computing the sum is a primitive operation, and dividing the total by this and assigning it to some part of the list. So this is a few constant operations or a few primitive operations. Still, if it's 1 or 4 or 3, it doesn't matter. And we have one here. The interesting thing is the inner loop. The inner loop has a counter, or has a range that is subject to j, which is the counter of the outer loop. And what we see is j starts as 0. So this is the range of 1. That means this line is run once for the first iteration of the outer loop. And these are eventually multiple primitive operations. But in the second iteration of the outer loop, the inner loop runs twice because j is 1 and then the range is 2. Then this one here next time runs 3 times. So first, this line is run once, then 2 times, then 3 times, then 4 times, up to n times. And all of this is summed together. And that's exactly what I have prepared for you in the slides. So we call this here line 7. This is the one we are most interested in. And this one is first run once, then 2 times, then 3 times. So we sum 1 and 2 and 3 and 4 up to n. And this sum here can be expressed as the following term. So the sum of I, where I is 1 up to n, can be expressed as n times n plus 1 divided by 2. Now, what would be the O complexity of this term here? O of what? You can send this to the chat or turn on your mic. This would be O of n squared. And line 7 counts the most, because here we see we have some O of n. This is run n times, but this is run n squared times, or O of n squared, just to be correct. So that means line 7 is the dominating one, because these other lines are, some of these lines are constants, O of n, but that line counts the most. And eventually we saw the only thing that matters in our O analysis is the largest term. So we would say our prefix average is 1 is O of n squared. And what we have done in the prefix average is 1, we've just implemented our equation. Do you think we can do this better? Maybe thumbs up or green reaction if you think we can solve this problem in better than O of n squared, green one, or red reaction if you don't think so. Various green reactions. So green means we can do it, and red we cannot do it. And it turns out we can do it. And for this, I will switch back. We will try again. We will just go back to our prefix averages 1. And we will try to do this a little bit better. Maybe we don't need the inner loop. Maybe we can calculate this total here smarter. And it turns out in Python, there is a sum function, and the sum function, we can put in some list, and these elements will be summed together. And what I can say is, well, actually, from my input S, I need something like this. These are these slices that you have also seen in the book. So in Python, we can index S0, but we can also use a slice. And the slice is something I start with index 0, then index 1, up to j plus 1, where j plus 1 is not included. So the upper boundary would be j. So I would look at all the elements from 0 to j. This is exactly what this notation gives me, or the slice. And then I have a slice of my list, and Python sums it together. I can also delete that 0, then the 0 comes in implicitly, but I just put it in now for the beginning that we're all on the same page. We can see if it works. We before called the prefix average as 1 on this, and see if we get the same result. And we get the same result as before. Do you think this has a better complexity? Green sticker means better complexity. Red sticker means not better complexity. So I only see agreements that this would have a better complexity. But it turns out this, and now one student says it's the same complexity, and that is correct. This algorithm does not have a better complexity. Yes, we have eliminated a loop, and loops are indication for complexity, but just an indication, because we also need to look at the individual statements. And somehow we need to implement this function sum, because this is definitely not just a constant number of primitive operations, because it depends on j. And it turns out that this sum here is still eventually 1, and then 2, and then 3, and then 4 steps. So just as before. So the sum, it was just helped us to eliminate the loop, but it has not improved the complexity because this is not a constant operation. What you will notice, it will, if you measure the running time, it will probably run a little bit faster um, than than you would think, or probably it runs a little bit faster than the prefix averages one, because um, when you don't write your loops, but you use some built-in Python function, this is implemented in low-level C, and this will tend to run a little bit faster, but it will not come with a better complexity. We will test this now. What we can do is, in IPython, you can run the so-called time. And so it's percentage time, and it runs this, and it tells us how long it took. So this took 6.91 microseconds. But now if I run it again for prefix averages 1, we see it takes 10 microseconds because it's the operating system, other work, and so forth. What we can do is we can run time it, and if we run time it, this experiment will be run multiple times. So we see this takes in average 596 nanoseconds plus a standard deviation of 27.8 nanoseconds. We can compare this to prefix averages 2 and see what happens, because then the experiment is just run many, many times. And we see it runs a little bit faster. Now, we can make that list larger that we are passing, because we're just passing a very, very small list. What we can do is we could have a list of random numbers, and I will quickly prepare this for you. So how can I just create a big list of random numbers? For example, in Python, I can import a random package, and I could say random.choices. It will give me 10 choices in a range from 0 to 100, where 100 is the upper asymmetric boundary. So I could have something like this, and I can now say I want 10,000, no, in the range of 0 to 100. I want 10,000, and I will store this. So I can say this is my data. And then I just run the prefix averages 1 again on my data. And we see how long it will take. So this experiment is run a few times. So we see for 10,000 integers here, it will take 813 milliseconds to calculate the prefix averages. And using the first very naive implementation, we're now using the more efficient, or hope maybe more efficient one, which uses internally the sum function from Python. And this experiment is also run multiple times. And here we see it actually runs with quite a constant factor faster. So about 5 times faster, because it just takes 172 milliseconds. But does a constant factor matter here for our O analysis? Yes or no? Yes, with yes, send a green sticker if you think this would matter for the O analysis, or red one if you think it doesn't matter or it does not matter for the one. So we see it does not matter. from the viewpoint of complexity. From the running time, yes, so we have two algorithms here with the same complexity, but one runs faster than the other one. Now the question is, can we implement this smarter? And it turns out we can implement this much smarter with a much smarter algorithm. Concretely, we will implement now prefix averages 3. And what we will do is we don't need to recompute this total each time from scratch. When you look before at how we implemented it, we always summed again everything together from the beginning up to our j. But actually, we could reuse the sum from before and just add something on top of the sum and then use that sum in order to continue. This is what we're doing now. So I'm saying my total starts with 0 and it's s of j. And rather than computing the whole sum, I will just use my current total and divide it by j plus 1. And this is the prefix average is 3, because each time what I'm doing in my sum, I'm just summing one more element, and here I'm just reusing the sum from the iteration before. What would be the O complexity of this one here? O of what? Looking forward to your answers, audio or in the chat. It's correct, it's O of n, because this loop runs n many times. But the operations in here, their running times, or the number of primitive operations in here, does not depend on n. So that looks great. And we will run it now. And actually, what do you think how long it will take to run this? Any guesses? So we've seen before, so we have these 10,000 random values. With our n squared algorithms, it took 813 milliseconds. With the optimized 172 milliseconds. What do you think how long the prefix averages 3 will take? How many milliseconds in average? You can guess some numbers here in the chat. One person says under 50 milliseconds. So about the square root. So I think one person says 13 milliseconds. I think it's maybe, I also, well, I think it's maybe around 10 to 20, but we will see how long it takes. I'm also curious. It depends obviously on the computer and the machine, but we see it's even much faster. So it's 0.3 milliseconds, in fact. So it's 367 microseconds. And it's still, the experiment was run 7,000 times. So we had 7 runs and 1,000 in each of the runs. So we get a very good estimate. So it's 367 microseconds. So yeah, actually much, if I look back, yeah, obviously much better than 10 to 20 because these were milliseconds. So I was also curious to see what the output would be. I also didn't think about it properly, but yeah, far under 1 millisecond. So we are at 367 microseconds. And this is now not just a constant improvement, but a squared yeah, we have just taken the square root of this and leads to a massive speed up, as we can see. So this is something we've tested now together for the prefix averages. And all we've just done here is also described in the slides. And there's a detailed analysis why this one here is O of n, but we've just discussed this together. Anyway, so this was the O complexity. And the O complexity is something we will need throughout the whole course, and you will need this throughout your whole career when you deal with algorithms and data structures. It provides us with an upper boundary. And a lot of algorithms and data structures courses are fine here and say you need O, nothing else. However, there are a few other notations that are still important. And like there is the O, big O, for an upper boundary, there is a big omega for a lower boundary. And all the same as before. F of n and g of n are functions that map positive integers to real numbers. And we say f of n is big omega, or just omega of g of n, if there's a real constant c that must be greater than 0, and an integer constant n0 that is greater than or equal to 1. And all we flip here is we say f of n is greater than or equal to c times g of n. So now the f of n is above the c times g of n, not below it, for all n starting that threshold. So what the big omega notation allows us to say is that a function f of n is greater than or equal to another function. So the function g of n is not an upper boundary, but a lower boundary in the asymptotic sense. And what we do here is we just pick the lowest order term. We still ignore constants on all of this, but if we say 5n to the power of 4 plus 3n cubed plus 2n squared plus 4n plus 1 is omega of 1, because we just picked the lowest order term, because it takes minimum that time. Now, I have a few more terms here. I will not write them out again on the whiteboard, but I want you to just answer this now step by step. So what is 5n squared plus 3n log n plus 2n? It's omega of what? Already got the right answer. It's omega of n. Obviously, omega of 1 would be correct too, but it's again a lower boundary that is not reasonable, and you pick reasonable boundaries like we pick for O, reasonable upper boundary, and we don't just pick the minimum lower boundary possible, but a reasonable one. So it's omega of n. Then 20n cubed plus 10n log n, it's omega of what? We already got the right answer. It's omega of n log n. So n log n grows slower. Then 3 log n plus 2 to the power of n is omega of what? Got the right answer. It's omega of log n, because this is the lower order term. Then 2 to the power of n plus 2 is omega of what? So for number 5. I saw the question here in the chat. We'll respond to it very soon once we've done this. One person says omega of 1. Omega of 1 is probably always true. But here I would say omega of 2 to the power of n, because this is the lowest order term. And one student asked for number 3, why we leave this 10 away, because we said we don't, both in O and omega, we don't care about lower order constants. I'll repeat it. We don't care about constants. For the O notation, we don't care about lower order terms and constants. And for the omega notation, we don't care about upper terms and constants. So because constants are always filtered out, because we have this C factor, and with that, this allows us to effectively ignore constants. And constants, computer specifically, maybe a computer is a bit more parallel than another one. We don't care about this because we only care about how this function grows based on n. And now the last term, 2n plus 100 log n, is omega of what? Omega of log n. That's correct. So you see, it's not that difficult. There's also some strange stuff you can do in mathematics. You can say like 3n log n minus 2n. What is that actually? And it turns out this is omega of n log n. If you care about the solution of how to solve this, this is here, but it's just some strange examples in the literature. But because this O and omega notation, it does not come from computer science. It actually comes from mathematics, and we apply it here to the study of algorithms, but the O and omega notation can be applied to other things as well, where you can also use minuses. All the terms we saw before, they only add up. And this is what we would do in an algorithm because we add up primitive operations. We would not subtract primitive operations because each primitive operation takes a little bit of computing time. But if you care about such strange stuff like 3n log n minus 2n and want to know why this is omega of n log n, you can find the solution down here. But for computer science, it's not really relevant because we only care about pluses, not minuses. Now we can actually combine both things we have just seen, O and omega, and we come to a so-called big theta notation. What is this big theta notation? We can say f of n and g of n are positive, our mapping functions as before, mapping positive integers to real numbers. Nothing new. And we can say that our f of n is big omega of g of n if f of n is O of g of n and f of n is omega of g of n. So f of n is both now. F of n is O of g of n and it's omega of g of n. In order to define this properly, we now need two constants, c prime, which must be greater than 0, and c double prime, which must be greater than 0. And we still have our threshold n0, which must be greater than or equal to 1. And for all n's that are greater than or equal to n0, f of n must be less than or equal to c double prime times g of n. So this is the upper boundary, but also the lower boundary where c prime times g of n is the lower boundary of f of n. So g of n is now an upper and a lower boundary at the same time, subject to our n's that are greater than the threshold and concrete constants. And here these constants, c prime and double prime, they may have different values. This theta notation is interesting because it allows us to say that two functions grow at the same rate up to constant factors. So not just an upper or a lower boundary, but both. So it just runs at the same rate within these constant factors. And this is quite interesting. There's also an example here as something like 3n log n plus 4n plus 5 log n. And this is actually theta of n log n. First of all, you would maybe think, well, there's a lower boundary and this is the upper one. But it turns out you can mathematically show that this term here is theta of n log n. If you want to know how to do this, look at this justification, study it on the weekend, because this is our term. And we can show that n log n is a lower boundary as well as an upper boundary for all n's greater than or equal to 2. And we have these constant factors. So here are these factors, 7 plus 5, so 12. And the other constant factor is 3. So this is maybe something you can study at home on the weekend. But why is this theta notation interesting for us now? What you would typically see in most of computer science and studying of algorithms, most of the time you'll be dealing with the O notation. And the O notation allows us to find an upper boundary, an asymptotic upper boundary. But the theta notation, so big theta, can sometimes be more helpful, and it can give us a better understanding. Imagine we have now an algorithm, some algorithm, and we want to count its primitive operations. And the number of primitive operations could be like this. So we would have some initial constant operations, then maybe some loop and a loop within a loop, and still a loop within a loop within a loop within a loop. So 3 loops in each other, for example. And we count like this the number of primitive operations. And what we can see from, if we have this T of n, we can obviously say that T of n is O of n to the power of 100. N to the 100, or O of n to the power of 100, is an upper boundary of our term T of n. We've said we can always pick bigger upper boundaries, which we don't want to do. We want to pick reasonable ones. So we can say T of n is O of n cubed, which is also correct because we just look at the largest term. But still, it's an upper boundary, and the theta of n to the third is a much, much better understanding of the algorithm than the O. Because what it says is, before our O of n to the 100, we say that T of n grows asymptotically no faster than n to the 100. N to the 100 is an upper boundary, given the constants and the n0. N to the third is also an upper boundary. And we say that T of n still does not grow asymptotically faster than n to the third. And T of n, and this is number 3, we can say with the theta notation that T of n grows asymptotically as fast as n to the third. Because this one says no faster upper boundary, but here we actually get something exact in terms of the complexity. It says it grows asymptotically as fast as n to the third. There's one student here asked if we could say that theta is in between of omega and big O. Well, it actually combines. The theta combines the big O and big omega notation. And like this, we can see that our algorithm runs asymptotically. So for n's after or s of the threshold runs as fast as something. So this actually gives us a much better understanding than the O notation. It only turns out for a lot of algorithms, it's sometimes quite tricky to find the big theta. So most of the literature you would see is O. And in this course, I would say like 90% of the time we need O, and the other 10% we need an omega and a theta, but most of the time we are probably dealing with O. When we looked at our big O notation, we said f of n is less than or equal to c times g of n. Now, if you change this less than or equal to sign to a less sign, then what you have is not a big O notation, but the small o notation. This small o notation is something like, we can say that 2n squared is small o of n to the third, because it's not a less than or equal to, but it's a real upper boundary that we cannot reach. So statement 1 would be correct, that 2n squared is o of n to the third, but 2n squared is not small o of n squared, because it's a less sign and not a less than or equal to sign. So there is this small o notation. If you ever come across it, you now know what it means, but I think it just plays a minor role in the research literature and in the books. And similarly to the small o, there's also a small omega, which would be a proper lower boundary that we don't reach. So it's something under our function, as the small o is definitely above our function. But it's just something, just a small detail. If you ever see a small o and a small omega, you know what it means. But as I said, most of the time you need a big O, sometimes a big omega or the theta. But I have hardly seen these small O's and small omegas in the literature, but they may pop up somewhere, so it's good to know what they mean. Then we're almost done with the notations for today, but there are a few more little things I want to discuss with you. There is also an O tilde notation. So what is an O tilde? It looks something like this. O tilde. It's something I only came across maybe some 5 to 10 years ago when I studied some more quantum algorithms. And what this O tilde notation does is, imagine you have something like O of h of n, and you have some more logarithm factors. So this would mean log n raised to the power of k. And the O tilde notation would just preserve our h of n, and the O tilde would ignore all the logarithm factors. It's something you see sometimes in quantum computing publications. Just to make that O more understandable, we say, well, the logarithm factors, we just want to leave them out, so we use the O tilde notation. So for example, here we would have n times log n times the log of the log n. We leave out all the logarithm factors and we say this is O tilde of n. So what would be, we have n squared times log n times the log of log n. What would be the O tilde? O tilde of what? You can send it to the chat. Would be O tilde of n squared. And similarly, for this last one, n times log n squared times the log of the log n would be just O tilde of n. Something you may see in quantum computing. So if you see an O with a tilde on top, you know what it means. And again, the most important one is the O notation. There's a small detail that you should know what it means if you hear about pseudo-polynomial complexity. We've always said we want a function f of n, and we had algorithms where the parameter that we passed was a list, for example, or some data structure to work on. Now, you could think about an algorithm that would do integer factorization. So we have an integer and we want to know what are its integer factors. And you could implement it in some language like this. So this is not Python, it's a different language, but it doesn't matter because what we say is we want to do the factorials and we pass a value n, like n could be 10, and we want to know its prime factors, for example. So 5 and 2 could be the factors for 10. And if you implement something like this, it could turn out that such an algorithm is one loop and another, and eventually, when you read, this was from a Stack Overflow article some while back, it could appear that this could lead to a linear complexity if you look at this algorithm. So suddenly we would wonder if integer factorization is linear, but in fact it's not. It's exponential, and that's why cryptography is so challenging. What has happened here in this problem, in the Stack Overflow article, we've noticed something that is called pseudo-polynomial complexity. Pseudo-polynomial complexity appears if you analyze this algorithm wrong and you think n is an integer that was passed, but in fact, we need to think that like a list is passed. And if the list is passed, then, and we implement this algorithm, then we would see that this algorithm takes an exponential amount of time. But by passing this integer, in fact, we get a polynomial time complexity, but it's just a pseudo-polynomial time complexity. It's not a polynomial time complexity. This is something you may not understand on the first time because we have just started to introduce the O notation, but all of this is explained very well in the Stack Overflow article. So once after the weekend you feel fine with the O notation, maybe go back to the Stack Overflow article and it's explained very well what went wrong there. And this is something you need to be aware of, that sometimes you can run into pseudo-polynomial complexity. And then, in fact, this will usually be an exponential amount of time that the algorithm takes because you looked wrong at the parameter that was passed. Because we think about a list of n elements, but if you pass the integer n, that makes a huge difference. This is the pseudo-polynomial complexity, and so far we've always looked with our studies today at the running time of an algorithm. But running time is not the only thing you need to think about, because your algorithms also need space in your RAM. If you just have a few constant values in your algorithm needs constant much space. But if your algorithms create helper variables, constant many, then you have a constant amount of space that you need extra. So always on top of your input. Because for the input, you anyway have a list already, but the space complexity addresses the extra space that your algorithm needs. And this is something you need to consider too, because your algorithm may need linear much space or even more than linear extra space. And sometimes you may just run out of RAM with some algorithms if you want to keep a lot of cache or a lot of helper variables to pre-process your input. What can happen is your running time has a better complexity, but your space complexity goes up. And typically, this is a trade-off you need to make in algorithms. You need to make a trade-off between space complexity and running time complexity. So maybe you have an algorithm that is not allowed to use much extra space, and it needs to recompute over and over a lot of things that may need extra or a bigger running time complexity. But if you can store some temporary results, maybe your running time complexity will go down, but your space complexity will go up. This is something we will see in numerous algorithms in this course. When we look at running time complexity, we will also study the space complexity, and it's a trade-off we need to make between the two. Now we're done with the complexity analysis chapter, and you're able to do all the coursework from section 8. I informed you on I learned that next week there's a lecture-free day when this course would take place. But next week we will do a double lecture, and the double lecture will be on, since there are no courses here on campus on Friday, we will meet on Zoom and we will have a double lecture from 9 to 12. If you can join the lecture, that would be perfect. However, since it's a lecture-free day, I know not all of you will be able to join. That's why there will be a recording as usual. And we will be doing from 9 to 12, we'll be looking at lists, which is a fundamental data structure. It's eventually a graph with some constraints. We will look at lists, we'll look at complexity of list operations. And then if you have questions on the lab problems after 12, I will still be in the Zoom session after the lecture for a while in case you have questions on the coursework. After the lecture next week, um, because we will next week we'll finish the list chapter, and we're doing this double lecture because I will be away in May for a business trip, and I need to make sure because we have a lot of public holidays in Germany in the summer term, and we would actually miss a lot of Fridays, and we would run into a challenging situation to finish this course with all the content. And that's why I want to have a head start, and we will have this double lecture next Friday. And you're welcome to join the live session. If not, there's a recording. And if you have specific questions on the lecture content, you can always come to the lab in the following week, so in 2 weeks, to ask me this question. Because the issue is this lecture is on Fridays, and there are a lot of Fridays that don't take place because of all these holidays. Will happen in a few weeks again. Plus, I will be away one Friday for a business trip. And that's why I want to have a head start, and you'll have more time also to work on the coursework. And for all questions you may have that you may not be able to ask next week, come to the lab in 2 weeks on campus and ask your questions there, and we'll study lists in detail next week. So I wish you a good weekend and enjoy your revision and the coursework, and see you soon. Take care and bye-bye.